So my name is Marzieh Ayati. I'm an assistant professor at University of Texas, Rio Grande Valley. And today I'm going to present a collaborative work between me and my colleagues in Case Western Reserve University about kinase-substrate annotation using networks of phosphosites and kinases. So as an introduction, the phosphorylation is basically a post-translational modification that regulates some cellular responses and phenotype. So this is a really important modification that we have for cellular signaling. So if you want to think about phosphorylation, you can imagine something like this, that we have these proteins as the smallest functional unit in our body, and then some modification is going to happen to these proteins and some phosphate compound attached to them. So we call these proteins substrate for the rest of this presentation. So there are some enzymes that does this job called kinases, that their job is basically, one of their job is attaching this phosphate compound to the protein. And we have some enzymes called phosphatases that their job is, one of their job is removing this phosphate compound from the protein. So these whole network of the kinases, substrate, and phosphatases, or if any disruption happens to these networks, for example, the kinase gets mutated and become hyperactive or hypoactive. So any disruption in this network can cause some serious phenotypes like cancer. For example, it has been shown in 70% of the patients with thyroid cancer, a specific kinase has been mutated. So that's why it is really playing an important role in cellular signaling. So the kinases specifically become a really important drug targets. As you can see, over time, the number of publications here on the x-axis, you can see the year, and on y-axis is number of publications related to the kinase inhibitors. That is increasing rapidly, the number of publications about them. And also, over the time now, the number of, I don't know if you can see my cursor, okay. Not this one. Okay. So here, over the time, the number of the FDA-approved drugs that their job is actually, the mechanism is kinase inhibitors, are increasing as well. That shows the importance of the kinases. So in the recent advancement that we had in the recent decade in the mass spectrometry technology allow us to have a high throughput analysis for the phosphoproteomics. So using this new technology, we can identify and quantify the amount of intensity of the phosphorylation of different proteins. So here you can see over the time the number of, so here in 2008, 2007 is when the mass spectrometry became high throughput. And then you can see the number of identified phosphosites is increasing rapidly over the years. So, but the important challenge in phosphorylation is which kinase phosphorylate which protein or substrate. So in 2019, there was this paper that published in Science Signaling that they were talking about illuminating the dark phosphoproteome. And in the abstract, as you can see here, it says the current biochemical and bioinformatics approaches have only identified kinases for less than 5% of phosphoproteome. So this is a really dark data that we don't know what happens, which kinase came and phosphorylate this protein, therefore which one is a good drug target somehow, right? So this is becoming a really big challenge here. So we have some gold data set that we have. Some of them are experimentally validated from Phospho-ELM and Phosphosite Plus. These are the main resources for the that tell us which kinase phosphorylate which substrate or kinase-substrate associations. But still we have that lack of computational analysis and computational methods, because you can see over time we identify more and more phosphosites. Therefore, our knowledge about which kinase is responsible and who caused this for phosphorylation is decreasing. For example, in 2008, they could identify 16,000 phosphosites, and for 21% of them, we knew which kinase is responsible to phosphorylate them. In 2011, we identified 42,000 phosphosites, and 12% of them, we knew which kinase was responsible. And in 2012, 1,000 and 10% of them, and currently we have more than 300,000 identified phosphosites, and our knowledge is so limited about those kinase-substrate associations. So it's been a really well-known problem and challenge in phosphoproteomics analysis. So there are some existing methods for these predictions. So the main one comes from the knowledge that we have that some kinase families tend to phosphorylate a specific sequence, a specific motifs in the protein. So using that knowledge that we know, okay, these kinase families are interested in specific motif like CCCGA, for example. So then they use this sequence-based method, and they use different machine learning algorithms to train these models to predict which kinase is responsible for phosphorylation. So there are different papers, different machine learning techniques using SVM, decision tree, artificial neural network, and so on and so forth. The problem with these methods that are just sequence-based level is that at the end, the output is, okay, now I know which kinase family phosphorylate these substrate. But the level of the information is at the family level. We don't know in that family of the kinases which specific kinase did the job, right? So that's why people came and developed more computational method, added some protein-specific information like the 3D structure of the protein, or they use protein-protein interaction network to improve and basically increase the specificity of the prediction, that now in this kinase family, which is specific kinase that, for example, is closer to the substrate in the protein-protein interaction network is responsible for phosphorylation. But as you see here, most of these computational methods use static information. So they are not depending on the tissue. They are not depending on the sample, cell lines that we are considering. So the challenges here is, first of all, we have limited knowledge about the structure of most of the proteins. Second, the cellular signaling is highly dynamic and transient process. So it might be different between the cells, between the tissues, specifically kinase-substrate interaction might be different between different tissues. So these challenges are out there. So here, in this research, we developed this new computational method. We called it NetKSA. The idea here is that I'm going to create a network that here, a graph, that every node in this network represents a phosphosite, basically that modified location of the protein. We call it phosphorylated site, that site of the protein that has been phosphorylated. So every node here is the phosphosite, and the connection between the nodes come from all different information that we have at the site level. For example, we have so many phosphoproteomics data generated from mass spectrometry. So we use that to calculate the co-phosphorylation and co-occurrence of the sites. If two sites has been co-occurring across, for example, 70 mass spectrometry study, we put an edge and connection between them. If two sites are belonging to the same pathway, we put an edge between them. If two sites have a similarity in the sequence, we put an edge between them. And if two sites are co-evolving also, obtained from the PTM code database, we put an edge between them. So we assume that this network is supposed to capture all the functional relationship between these phosphosites. On the other hand, we create another network. In this one, every node is a kinase. That kinase that is responsible, and their job is attaching phosphate compound. And the connection between them come from if the two kinases are physically interacting based on the BioGrid database, or if two kinases are in the same biological pathway based on the SIGDB database, or if two kinases are from the same family. Let's connect them as well. So because we want this network to capture all the functional relationship between the kinases. So now from this network, what we do, we create the node embedding. You can think about node embedding as if we are vectorizing the graph. So basically, every vector here is going to show the relationship between that node and other nodes. So we use different node embedding methods. And so we present every node in the graph using a vector. And then we use the phosphosite plus as the gold data set that they are valid kinase-substrate association. And we did the cross-validation, and we test our algorithm. But the drawback of these prediction methods is that always, and you might see it in other biological analysis as well, always rich gets richer and poor get poorer. If we have knowledge about some proteins, they keep popping up in our analysis, right? So the same thing is happening here. So in this graph, you can see that it's so small you may not be able to see, but basically there are some kinases that we know about more than 300 substrate for them, but majority of kinases have basically less than 10 known substrate. So when we train our model using these biased databases, that, for example, some kinases are so rich. We have so much information about them. I know so many of their substrate. So when we move to the training model, we're going to face that issue that we're going to favor them. We're going to rank them always the causal kinase, right? So this is the issue that most of these computational methods are suffering from. So in order to tackle that challenge, what we propose is kinase stratification. So we come and say, why do you want to put all the kinases in one bag and rank them and find which kinase was responsible? Let's categorize these kinases based on amount of information that we have about them. For example, if they have more than 20 known substrate, let's call them rich kinases. If they have between 4 to 20, and these are random numbers we just pick based on the distribution, we call them average kinases. And if we just know less than 4 substrate for these, and majority of them we just know 1, so we call them poor kinases. So with this classification, so now if we want to rank the kinase for the phosphosites, we're gonna go to that category and we say, okay, which rich kinase is responsible, which average kinase is most likely to be responsible, and which poor kinase is most likely to be responsible. So that when the biologists come and look at these, they can decide that I'm not gonna go always with the rich kinase. I might want to test that poor kinase and see if that's actually the main kinase that I have to consider. Also, as you can see in the results, so basically, we compare our NetKSA method with 2 other state-of-the-art method, Kineme Explorer and Link Finder. And so you can see overall, our method is doing better than the other 2 functions. But what is important here, when we apply that kinase stratification scenario on every method, these basically light area are the improvement of their performance for every method. So we applied in all the methods, and we saw that we actually could improve the performance of the prediction or ranking of the kinases across all these methods. We also wanted to investigate, our network models basically has any influence on our prediction. So for that purpose, what we did, we permute our networks. So basically, we break those relationships that we built based on the known knowledge. We permute our network, and we see, oh, how is the performance if I have a random network, right? So we permute the site association network, we permute the kinase association network individually, and also we permute both of them. And you can see actually network can contribute to the prediction that we have, because the performance of the algorithm using the original network is better than the performance of the algorithm on the permuted ones. So as the conclusion, integrating different data sources, static and dynamic data, and network model help improving the prediction of kinase-substrate association, and also kinase stratification and predicting kinases in different categories help improving the prediction performance. So if you are interested to know more about phosphoproteomic data and also other algorithms and other challenges here, we have a workshop on Sunday, 9 to 1. So you're gonna hear my voice for a couple of hours, but if you are interested, please sign up for the workshop. With that, I would like to thank my collaborator at Case Western, Dr. Koyotok, Dr. Chance, Danny, Serhan, and Philippa, and our sponsors. And thank you so much for listening to me. If you have any question, I would be happy to answer.
So thank you, Marzieh, for your talk.
Sure.
So we have time for questions. Please come to the mic.
Yes, thanks for your talk. I was wondering if you have run algorithms in your graph, for example, PageRank or Lubine community finding, and what have you found?
So in those networks, so that's a great question, thank you. So this network that we create, okay. So we did different, so for the kinase prediction, that, for example, the node embedding, you can use the PageRank for node embedding, right? So page ranking is basically one of the methods you can find a node embedding. And we actually tried that as well as one of the node embedding method. We tried different node embedding methods, and one of them was PageRank to see what we get over there. But about the community detection, that's a really interesting question. So what we did actually, we applied the community detection on these networks in different concept though, but we identified that these communities, these modules that we identify are associated with the subtypes in the cancer. We specifically focus on breast cancer, and we saw these modules are associated with the subtypes like the HER2 subtypes or basal subtypes of the cancer that shows that, that you may not see that level. So if you come to the workshop, we talk about that as well, that sometimes in transcriptomic level, you cannot see the subtype signature, but in the phosphoproteomic level, the module that you mentioned show that there is some association between them and the subtypes as well. Great question.
Okay, thank you.
Thank
Great
you.
talk.
So I have a
Is there any question?
hello
Sorry.
question. Yeah.
I thought
We are not
the
finishing.
next speaker was waiting here. I was like, oh, I'm out.
I have a question regarding the site association networks and the other ones. You mentioned that you have 3 different inputs or 3 different evidence in order to build the networks.
For
like
the
a
sites, we
pathway.
have 4.
Sorry?
For the sites, we have 4.
Exactly.
Yes.
Okay. Pathway, sequence similarity, and PTM.
And phosphoproteomic data,
code.
co-occurrence, co-relationship. Yeah.
Exactly. My question is if in order to build the network, are you weighted some of these evidences or you have maybe an average score, or how do you put a threshold in the edges?
Yeah, that's a really great question. So yes, we actually looked at this as a binary network. So we put a threshold for the co-occurrence, for example, for the co-occurrence that comes from the phosphoproteomic data, the dynamic data. So we calculate the p-value and we put a threshold based on the distribution of the data that we have, because we didn't want to have a really dense network either, because then there's so much noise in the network. For the sequence similarity as well, so we did the sequence alignments and then we put a threshold on the similarity between them. So yeah, we didn't have the weighted network, but for the subtype analysis, we used the weighted network as well, actually. But that's a great question. Great.
Thank you.
Thank you.
So, question? No, we have time. We have a minute.
Okay.
If you have.
I have a question regarding what's the usual dynamics of a phosphorylated site? Like, if you take into account the expression of the phosphatases and the kinases, like if it's phosphorylated, then it stays that way for generations, or it's usually dephosphated very quickly? What's the usual?
So more than 70% of the proteins have been phosphorylated in different contexts. So the problem that we have, and I want the whole community to contribute to that, is that in phosphorylation, the bad thing is people don't focus on the phosphorylation in a normal tissue or non-cancerous or healthy person. So most of the data that we have are for the cancerous people, right? Cancer tissues, or we don't have really a normal phosphorylation to see that, okay, which ones is basically, and I want the whole community to contribute to that and start focusing on generating more data related to that, because we know that more than 70% of the protein can be phosphorylated, but in general, but which ones is associated with the disease, because we don't have really good samples for the healthy people or healthy tissue. So we don't know, that's a challenge. That's one of the challenges that we have, but that was a really great point. Yes. Did I answer that 70%?
Yeah, thank you.